lecture is going to be largely qualitative. You know, engineering is a lot about operating a calculator and doing calculations, but you have to be able to understand the foundational principles to apply the method to new situations. And so it is really important that you understand the background information behind some of the methods that we're using. And so it's great that you can run StormCAD, but it's also really important that you can do the rational method without a computerized tool. And it's also important to just know the basics of hydrology so that you can know when certain methods do or don't apply. So I'll have those exams finished and we'll go over them in class on Friday. And your next homework assignment, number 6, that's due a week from today. Already you could solve the first few problems on that assignment based on what we went over in class on Monday. Now we're going to continue talking about some concepts related to runoff today, and specifically the shape of hydrographs. So today we'll be talking about stream response. Some of the reason why stream response is important to study is in part because, remember, water is a resource. It's not just always something that's causing flooding and problems and has to be conveyed away as a waste product as quickly as possible, but water is something that's consumed for personal use, industrial and commercial uses, and so we want to know between when it rains and when the runoff arrives, how long of a delay there is, and how long might the water last in the receiving body between storms, and how quickly will it evaporate. So there are water supply issues that we have to be familiar with. But then sometimes water is that thing causing damage that we have to be prepared for, and so studying stream response will help us to improve the precision of flood prediction and forecasting how high the water levels will get. And here in Huntington, the Army Corps is able to predict with really amazing precision exactly what time the river will crest, how high it will get. And in large part, that's because they have a series of dams upstream on the river, and so they can control the flow by releasing water through those dams. But then it's also simply because they have really good weather stations and models that predicts the relationship between rain and how much water will be in the streams. And so forecasting is important to avoid damage and give people enough of a heads up to evacuate areas that may be affected. High water levels can also affect the water quality. And so the water company has to be aware of what the flow rates are going to be like in a stream, because the turbidity may change over time, and what kind of pesticides and fertilizers get into the water varies based on what kind of storm events there are. And so here in Huntington, they change the recipe they use for cleaning up the drinking water depending on the seasons and depending on what the storm characteristics have been like. There are certain times when they're injecting powdered activated carbon to absorb pesticides that otherwise could be harmful to human health, and there's other times that they don't. And so they keep tabs on what's happening with the river because it's the source of the product that they make. So when I say stream response, what I mean is the relationship between input to the model, and so the input to the model is precipitation, and we visualize that with the hydrograph. And so a hydrograph has the depth of the rainfall on the vertical axis and some measure of time on the horizontal axis. And so that's what goes into a model that predicts stream response, and what comes out would be a hydrograph. Now, a hydrograph can also be measured directly. It's not always just something that we're predicting with a model. You can set up stream gauges next to a river and measure over time how deep the water is, and based on the known water depth, you can figure out what the flow rate is, the discharge, either by using something like Manning's equation or through surveys of the channel slope. And so sometimes it's directly measured, but a lot of times what we're going to be doing in this class is trying to take rainfall data and predict what is going to happen in the stream over time. And so we want to know, how high will the peak get? We want to know things like, how long is it going to take for the flow rate to get down to its pre-storm levels? And how long of a delay is there between the beginning of the storm event and when we see the peak? So those are some of the things that we like to predict with stream response models. Now, there's a lot of physical factors that determine the shape of this curve, that determine how long the gap is between when the rain occurs and when the peak exists. A lot of physical factors that describe whether this will be a tall peak versus a broad peak. And so we're going to talk about some of those physical factors that influence the shape of the runoff hydrograph. Of course, the precipitation characteristics is going to affect this runoff hydrograph. So if you have a storm that's relatively quick and it occurs rapidly, then that would lend itself to a flashy peak. But if it's one of those coastal storm events where it's just slow and steady throughout the entirety of a day, then the hydrograph shape is going to be a little bit different. And so, of course, precipitation characteristics is part of it, including what direction the storm is moving over the watershed. We'll talk about more about how that could change the hydrograph. But the watershed characteristics are also very important. And so, for example, what route the water takes as it runs over the surface, enters shallow concentrated flow paths, and then gets into mainstream channels. And so sometimes the water will be able to move very directly, and other times there's a lot of barriers in the way. And so we have to have an understanding of the sinuosity of the flow path. That is, how indirect and circuitous the flow path is before it gets to our outlet. And we can simplify models of that stream network and try and develop schematic representations of how the stream is getting bigger as you move downstream, and there's additional channels that are branching into it. And some of the models that we'll be learning this semester, the computerized tools that we use for modeling, kind of conceptualize a watershed like this, where you'll count how many upstream channels you have of a certain size and how much contributing area, and then you kind of predict the quantity of the flow based on the total cumulative area upstream. So this is not what you'd actually see in a watershed. This is just a schematic or a simplified representation. But what you actually maybe would see as far as watersheds, if you were looking from above with a topographical map, might seem more like this. And so this is showing different types of drainage basins, and these different shapes of the flow paths are related to the geology. And so most of what we see in this region of West Virginia are dendritic networks, where you can see that the streams kind of are meandering, and there doesn't seem to be any regularity or any consistent flow direction, in contrast to this trellis pattern. And so in this trellis pattern, you can see that here is a stream that's not meandering, but it's mostly moving in the same direction, and it's receiving flow in the opposite direction. And so, you could infer from this that there's a ridge line here at this location of the red cursor. This is the high point. And so there's a long ridge that's probably something like a resistant rock, a rock that's resistant to scour and erosion, whereas the low points, which is where the water goes, this was some geological characteristics where it was less resistant to erosion, maybe a looser soil compared to the rock that was at the ridge line. And so the geology of the soils and the rock in the area is going to have a big influence on the shape of the streams. And so in coastal areas, you can see a trellis pattern on a mature coastal plain where you have pretty regular flow direction for the mainstream channels, and that's because over the ages, all of the fine and loosely held sand patterns have scoured out to sea, and occasionally in West Virginia, in parts of the state that have a lot of rock, you can see these rectangular patterns which have, you can see a lot of 90-degree angles where rock fracture causes low points, and the streams are following fissures in the rock. So this is just one thing to be aware of, is that when there are these numerical ways to describe how windy a flow path is. And just knowing that in the abstract is fine if you're putting it into a numerical model, but you also have to know that there's some reason why a flow path would be windy versus maybe a straighter flow path like this, where there's going to be the possibility for even faster moving flow because the water momentum carries on in the direction of flow. Our book talks about the idea of stream ordering, where a first order channel is one that just only receives surface flow. A second order channel, you can see, is where two first order segments have come together. And then a third order channel would be where you have at least two second order channels coming together. And so this is just a useful way of stratifying how important different stream branches are, and also predicting in advance how often they might be full. There are some streams that always will have water in them because there's so much upstream area, or because of things like interflow coming from groundwater and re-emerging at the surface. And so a stream that is perennial is one that always has water flowing in it. And so we'd expect a higher order stream to be perennial, whereas an ephemeral stream is one that only has water in it immediately after the storm actually occurs. And so a lower order stream, like a first or second order stream, maybe is going to be dry unless it's immediately after the storm event. And so I have an ephemeral stream in my backyard where I can go hike around on a dry day and don't get my feet wet, but then during the rainstorm it sounds like a roaring river back there because it's so steep and the water moves really quickly through those ephemeral streams if you have steep conditions. But it's first order, where there's not a lot of upstream contributing branches to the streams near where I live. And an intermittent stream is just kind of in between. You'd, during the wet season, have flow that stays in the stream between specific storm events, but then in the summer months or during dry periods, those streams would maybe be empty. And so here's an example of a perennial stream. This is the Provo River out in Utah, and it's some of the, I don't know, most famous trout fishing country in the United States. Always has flow in it because there is a lot of snow and ice runoff that continues even through the summer months. And so it would always have flow in a perennial stream like that. Here's an intermittent stream where only during the warm months, when there's runoff from the high altitude mountain, would there be water going through this one, but this doesn't have enough upstream area to always be full. And then an ephemeral stream is, of course, one that's only going to have flow in it immediately during a rainstorm event. And so this is relatively small. You can see that this ditch isn't going to be draining a large area. You know, from comparing the size of it to the size of a tree trunk, you can tell that there's not going to be a lot of upstream area. This figure, it's a comparison in your book that is highlighting the difference between, during a dry period, how far the stream network reaches into a watershed. And so these thick black lines represent the locations that actively have water in it. So during dry period, you'd have to have a really large upstream contributing area with just a little bit of surface, over the surface flow, and mostly it would be groundwater seepage that is feeding the flowing stream. But during rainfall events, during wet weather, this network extends deeper into the same watershed. And so this is the same watershed, just under two different conditions. When it's wet, then the channel goes further upstream. There's more of the wet seepage areas. And so we have to be mindful of how long it's been since the most recent stream and trying to compare what we see now to how the conditions may be different after it's been raining, and plan accordingly. So if you go into the field and you do a survey of the channel, then it may not always look like you're seeing it on the day of the visit. You know, the storm network could be extended quite a bit further into the watershed. This is, on the right side, a watershed in Illinois. So just in case you don't know where Illinois is, of course, it's here in the central United States. And if we were going to zoom in on the entire state of Illinois, the watershed that we're looking at is only a small fraction of the total state area. It's maybe like 5% of the state of Illinois is this overall watershed. But what we're going to look at is during a certain storm event, if we had a total amount of rainfall of 1.47 inches. So that's the kind of storm that you'd see a few times during a year. It's not, you know, like a 2 or even a 5-year storm. This is 1.47 inches. You'd see that kind of a storm several times during a year. If you zoom in on just a tiny small fraction of this watershed, and so if you're looking at a drainage area that's 0.2 miles, then there's going to be a very quick response between the rainfall and the runoff. So here's the hydrograph, and look at how it has multiple peaks on that hydrograph. And so the first peak is corresponding to this first burst of moisture, and so it was rainfall and response. And then there's a period where it wasn't raining for a bit, and you can see that the hydrograph is getting lower because there's no new moisture feeding the flow into the streams. But then it goes up again immediately after this burst of precipitation. So there was just another microburst that occurred, and then same thing, that the limb recedes, the flow rate's getting lower, but then we have this largest of all the storm bursts during the overall event. So a period where the rate of the storm was 4 inches per hour, but it wasn't for very long. It was maybe just for 10 minutes or 15 minutes, but it drives the peak a bit higher. But the thing to remember is that when you have a small drainage area, there's not much of a gap between how long in time between the storm event and the peak. And you can differentiate these individual peaks and tie them to the specific storm event that caused it. But if we zoom out a bit further to a larger drainage area, so this first one was the area encompassed by this small circle. It was a small sub-unit of the overall watershed. But let's zoom out to a larger area, now 3.2 square miles. What we see is still evidence of these individual components of the storm, but it's muted. You can see that the peaks are suppressed. And the reason for that is that when you have this larger basin, that the water has to flow through a channel, and as the water flows through the channel, it slows down. And just think about what would happen if you took a glass of water and you poured it into a gutter, like the gutter that a rain gutter on a house. If the gutter is relatively short, if it's only 10 feet, and you pour out the water over the course of 3 seconds, so you're pouring a glass of water over the course of 3 seconds into a short rain gutter, then at the end of that rain gutter, the water will come out in pretty close to 3 seconds. Maybe it's because it's spreading out a little bit and it's delayed and slowed down as it flows over the surface of the metal in that rain gutter. It maybe will take 4 or 5 seconds. But now lengthen the rain gutter to 100 feet, and even though you pour it out over 3 seconds, it's not going to all empty at the end of that rain gutter in 3 seconds. It's going to have a little trickle of it that comes out, and then more, and then it'll be draining for just a longer period of time because the water that has wet the initially dry rain gutter is slowed down and delayed, and the shear stress that's applied by the stationary surface to the flowing water just delays it, such that they call that effect routing. The delay that water experiences as it moves through a network. So here we're seeing the effect of routing. So there's a delay time between this first burst of water and the peak. See that the peak is further away in time, but also the height of the peak is muted because it's just been kind of smeared together with the other rainfall events. And that same kind of routing effect occurs as the drainage area gets progressively larger. So now if we talk about a 16-mile drainage area, we don't see any of the individual peaks anymore. It's just here at the outlet of the 16-mile drainage area, there's an even longer delay between when the rain occurred and when we see the outflow. Now, the flow rates themselves may be higher. The discharge here, you can see cubic feet per second. In the first watershed, we only saw the discharge getting up to maybe 13 cubic feet per second. The peak for the larger area was 50 cubic meters per second. So the overall flow rate is higher because the area is larger, but the arrival time, as you progressively increase the drainage area, is further delayed, and the individual peaks kind of smash together. So that's one of the trends to know about, is that as watershed area increases, there's more of a delay and the individual peaks are attenuated. Some of the other important flow mechanisms is that water can, when it falls at the surface, remember, either infiltrate down into the soil or it can flow over the surface. And so overland flow that happens when the soil is saturated and it continues to rain is called Hortonian overland flow. So it is the overland flow where the water stays at the surface. But there's also saturation overland flow. And saturation overland flow occurs when there is groundwater that's re-emerging and then re-emerging from underground and then is flowing over the surface. And so this kind of illustrates the difference between Hortonian and saturation overland flow. The Hortonian overland flow is the water that stays at the surface and flows towards the stream. But when it rains and the water table is elevated, then you can see that some of the water that's underground in the aquifer may re-emerge at the surface and then flow from the surface into a stream. So I've mentioned before those wet areas at Barbersville Park, where you know, if you're walking around on the hillside, in certain places your feet would stay dry because the water table isn't at the surface. But then other locations, the water table is at the surface, and so that saturation overland flow is what occurs in those perpetually wet areas, or the wet areas that emerge when it's been raining. So here's just another illustration of the subsurface and how water that's underground can get into a stream. When it goes directly into a stream without first going to the surface, that's what we call base flow. So this return flow was at the surface and then it flowed into the stream from above, whereas base flow gets into a stream directly without re-emerging at the surface. And so we have our saturated water table beneath this dashed line, and so the water is moving laterally towards the stream. So that's base flow, whereas the return flow was what emerged at the surface. Now, when you've got wet weather, remember that the water table gets higher, and so there's going to be more base flow and then also saturation overland flow. If we look at a hydrograph, we can sometimes tease out what part of the hydrograph is associated with what component in the stream. So the base flow is the water that would be in the stream even before a storm event occurs. So it's the water that isn't going to go out even after it stops raining. It's the groundwater feeding this this first quantity, the base flow, you can see that the interflow, which is the movement of water that was beneath the ground surface, but it's in the vadose zone, which is the unsaturated zone above the water table, is the next component at the foundation of the hydrograph. But then most of the peak that we see is the saturation overland flow. The shape of the hydrograph is influenced by a lot of factors. And there's a quote in our book here talking about abstractions. Remember, we talked about abstractions in class previously, and some of the abstractions that are important are interception, surface wetting, local depressions. And so once all of those have been satisfied or accomplished, then the excess water that still remains that hasn't infiltrated will begin to flow over the land and eventually gets into the drainage channel. So how high the hydrograph gets and how broad the peak is or how narrow the peak is depends on all of these factors, and we'll talk about some of these individually. And the more of these factors we're able to account for in a model, the more accurate the model is going to be. So think about the easiest model you've seen so far for predicting what a hydrograph looks like. Q equals CIA. And the rational method has time on the horizontal axis, flow rate on the vertical axis, and it just assumes a triangular distribution. You get up to some peak flow rate at a time of concentration. Now, the rational method C value is taking into account the relative amount of impervious area. So you could see that it's taking into account the vegetation is represented in the C value. And we have different C values depending on how the slope of the watershed is. And of course the A is represented by the drainage area. But there is some factors that the rational method doesn't take into account, like the slope of the channel. And so if we have a watershed, like we have a watershed with a lot of streams in it and so on, Q equals CIA doesn't have anything talking about the characteristics of the stream inside the watershed. It doesn't reflect the length of the stream. It doesn't reflect how closely spaced the channels are or the roughness of the stream. It doesn't really have any of the effects of routing accounted for. And so it's just going up to a triangular distribution regardless of lots of variation in these different parameters. So let's talk about how each one of these parameters would affect what the hydrograph looks like. So remember, what we're looking at in this hydrograph is the runoff. There's a certain amount of rainfall, and then the watershed responds to it. So in previous exams, by the way, I gave a hydrograph, and I said, draw the new hydrograph if the watershed was steeper. And so this is an example of a gentle watershed slope where the water moves over the surface relatively slowly. Then the peak isn't going to be very high, and it'll arrive more slowly than if you had a steep watershed. So what we have in West Virginia is some of the steepest watersheds in the country, and so we're accustomed to seeing big peaks that arrive quickly. So when it comes to the factor of watershed slope, you can see the contrast between a gentle, relatively mild slope and a steep slope, and what effect it has on the runoff hydrograph. Okay, now think about in the channel that's carrying the water, what if you have a relatively smooth surface versus a rough surface? And so a rough surface is going to provide resistance to flow, so the water can't reach the same velocity as it could with the smoother surface, like an engineered surface like concrete or a paved asphalt channel. If it's less rough, then you're going to have a quicker peak and a taller peak. than if some of that flow energy is exerted overcoming the resistance of the channel. So you can see the hydraulic roughness effect. If you have intermediate storage, so if the water's flowing over a hillside and it encounters a pool of some sort, so this could be like depression storage or puddles, or it could be specifically put into place just to slow down the movement of the water. But when there's storage that has to be filled up before the water is able to move downstream, then that reduces the peak and moves it further to the right. Drainage density. A high density would be like, so I already have this hydrograph on the board here where it's showing one main stem and then 3 branches. And so before water can get to the main outlet, think about the path that it has to go over the surface some distance, and then finally it's in the channel where it can flow more easily. Well, if you have more defined channels at a greater density, so more channelized flow and less surface flow, the more streams that you have in the watershed, the water doesn't have to travel as far before it encounters a stream, and then it begins the quicker transit towards the outlet. So this is just showing if you have a high density of streams, meaning just lots of channelization in the watershed, then that would give you a higher peak that is sooner compared to a low density of streams. And then finally, the overall length that a channel has. So a shorter length, meaning less meandering networks. So we were looking at the trellis patterns compared to dendritic networks. So if you have a flow path that's short, then it'll arrive at the outlet more quickly than a longer flow path. And so it's not just the time of concentration, though, it's also that the peak is lower on the longer length, because think about that long trough. And if it has to flow through a longer path, then not only is it delayed, but it's also attenuating the flow. It's diffusing it. All right, now let's look at differences in rainfall. This is a front-loaded storm where most of the intensity occurs early on, and then there's a tapering intensity later in the storm event. So then that would cause a front-loading in the hydrograph that is opposite to what you'd experience if you had just a little bit of wetting followed by the bulk of the storm occurring later. So you have to think about the temporal distribution of the rainfall, just how it may be different over time. And so if you just have daily rainfall data, maybe these two storms look pretty close together, 1 inch versus 1 inch. But sometimes you have to think about how that 1 inch over the course of the day could be concentrated either early in the day or late in the day, and then how that would affect the hydrograph. So these could be hydrographs from about the same quantity of rainfall, but the time of concentration is totally different because of when the rainfall occurred. This next illustration is just showing that sometimes a storm doesn't cover the entire watershed. Even if you have a rain gauge here where it is storming, sometimes the rest of the watershed is dry. And so look at storm A is just in this faraway reaches. And so the water that gets into the channel at this location has to travel through a dry stream. And water is going to travel through a dry stream more slowly than in this other illustration where it's wet everywhere in the network. The peak is much sooner because the water is falling everywhere in the network, and so the stream becomes wet by the flow that's immediately adjacent to the stream at every location, compared to in this earlier case where as the burst of water makes its way through the network, it's having to do the work of wetting the stream ahead of it. So storm B arrives sooner, and of course there would be a larger quantity simply because more of the watershed is being inundated with water. Think about if water was if a storm was moving either from B towards A, or if a storm was moving from A towards B. So it's just this storm that's only covering part of the network, but it's not over the whole network at the same time. And that's what storms do, is they travel from place to place. And so you could see differences in the hydrograph where it's the same amount of rainfall, but just the travel direction was slightly different. So if it's moving from B to A, think about why the peak would be higher. Like, what could be causing the higher peak? It's because the storm is basically traveling along with the water. So more of it arrives at A at the same time, because the water that falls at this outer edge is traveling towards A at the same time that the storm itself is traveling towards A. So it's just all getting here at location A at the same time, compared to when the storm movement was opposite to the direction of the flow of water at the surface. Our book, by the way, goes into a discussion of each one of these different characteristics and effects. And so I'd encourage you to read through the book and think more about this and try and commit these different trends to your memory. All right. I've used the phrase rainfall excess before, and when we've looked at a rainfall hydrograph like this, and we draw the typical curve for declining potential infiltration. So this is lowercase f. Remember, both rainfall and infiltration will have units of length per time. So inches per hour, centimeters per hour. It's the area above the infiltration curve that's the rainfall excess. So the rainfall excess is the water that's over and above the abstractions and infiltration. So it's what's going to cause the runoff. So infiltration is decreasing over time, of course, because as more water gets into the subsurface, the suction head decreases. So the dry soil initially has a high suction head. As the pores are filling with water, the suction head is decreasing. So that's just to reiterate why the infiltration rate is declining over time. And remember, a hydrograph is the illustration of the rainfall, whereas the hydrograph is the runoff over time. So what we're going to do in the next coming classes is we will put a certain rainfall, a certain storm, through a process of subtracting out the abstractions and infiltration. And so we want to determine how much rainfall excess is there. And then we have to have some way of taking the rainfall excess and translating that into runoff. And the simplest way to do that is with something called a unit hydrograph, which I'll tell you a little bit more about on Friday. But it's this step from rainfall excess to hydrograph that there are so many different methods to do. Lots of different empirical extrapolations based on the shape and size of the watershed, based on known observed behavior in adjacent watersheds. If you happen to have a stream gauge in the vicinity, you can sometimes infer the behavior of that other watershed to the one you're studying. So we're going to go through a lot of different methods for linking the rainfall excess to the shape of the hydrograph. And then the final step that this is showing is just trying to figure out, when you have a hydrograph, how much of that is base flow that would always be in the stream due to the groundwater, and how much of that runoff is due to the storm event itself. All right, so we're going to start on this unit hydrograph when we get together on Friday. That's it for today. Just the reminder that your next homework assignment, number 6, is due a week from today. All right, so I'll see you on Friday and we'll go over the exams.